So the topic is curve sketching. Of course, it's crucial that you examine a function for its significant points. And as the first example, to give an overview, I'll take the course of a polynomial function, which is also often called a rational function in school. And I'll go through the different points. For example, you have this here, which you might know, which you already learned at the very beginning with functions, back then with linear functions and quadratic functions. The y-intercept, which you get by plugging 0 in for x in the function equation, and what comes out is the y-intercept. If we have the y-axis here and the x-axis here, then we have the x-intercept. We see a total of 1, 2, 3 intercepts on the x-axis here. Those are the zeros which we get by setting f to 0 and solving the equation accordingly. That's where we encounter the famous math vocabulary. Recognize the math term, danger averted, 0. What kind of function do we have there if we have a curved progression here, a polynomial function? Which solution method do we use if we substitute accordingly the x-intercepts? That is, we also have the ratio at the edges of the domain. We don't have any restrictions here, like with rational functions or logarithmic functions. So we go from minus infinity to plus infinity. That means at minus infinity and at plus infinity. There we now have to examine what the graph does. And we see here, if we keep moving further to the right on the x-axis towards plus infinity, what does the graph do there? It keeps going further upwards towards plus infinity. And that's the limiting behavior. In this case, the limit as x approaches plus infinity for the corresponding function. And on the other side, as we can see here, there's still the arrow. You can see it goes downwards. Here we're looking at the limiting behavior. The limit as x approaches minus infinity, the function equation. And that's where the graph, as I always say, comes from below, that is from minus infinity. That's the limiting behavior, with the limiting behaviors on the left and right, the corresponding zeros, and the y-intercept. You already have a rough idea of how you can sketch a polynomial function in this case. Of course, it continues with the key points. And the first thing we learned was derivative. Yes, we know that the derivative indicates the slope. And we have some key points here. One up here and one down here. I'll just call this up here the peak. And down here, this is the valley. And there's something noticeable about these key points. The slope there is actually 0. Yes, you can imagine it like this. You're standing up here on the peak, up here on the mountain, and at first nothing happens. That means the slope is 0, and if you lean forward just a bit, you go down the mountain. And down here at the bottom of the mountain, the slope is 0 again, and the term is slope 0. Yes, that should actually be the indication of how to identify these special points. We need the first derivative and set it equal to 0. Yes, that means the first derivative gives the slope, and the slope is 0. We are looking for the key points, so we set the first derivative equal to 0. Then there's the further behavior, the analysis. Is it a maximum or a minimum point? There are also special points, such as the saddle point. Yes, I'll do that up here. Yes, that means we have a slope of 0 here, but then it continues to go upwards. So-called saddle point. That means here the slope is positive before and positive after, while at a maximum point the slope is positive before and negative after. That means we can either calculate the whole thing using the monotonicity table, which I will of course explain in detail again, or you can also use the value of x that you found and check it using the second derivative. This is about the necessary and sufficient criterion. For now, I just want to give you an overview so you understand which key points there are. And then, of course, there's another key point. That's where there's a change in curvature, which would be here. Here, I'm steering the wheel to the right, and then I steer the wheel to the left. This is where the curvature changes. And that's the corresponding inflection point. We find it by setting the second derivative equal to 0. And I'll also illustrate this again in separate videos, showing graphically how the relationships between the graph and the derivative graph work, both the first and second derivative graphs, and sometimes even the third derivative graph as well, so that you can understand why we set the second derivative to 0 here. And with all these values, you can then create the drawing for the corresponding functions perfectly. What comes on top of that, of course, after differentiation in calculus is integration, which means finding the antiderivative. Is the antiderivative basically the inverse of the derivative function for you? The antiderivative is mostly used to determine areas like here, the area enclosed between the graph and the x-axis between these two zeros. For that, we need integral calculus. That would be the integral here. From a to b for the function f, interval x dx. dx equals the antiderivative and then the interval from a to b. And here you now have an overview of everything that's relevant for curve sketching.